Okay, so welcome back. Uh, so we're now going to look at an example of one of these games. So you might be thinking to yourself, well, hey, this ought to be a pretty fun topic, right? I mean, game theory, it literally contains the word games. Everybody loves playing games. But I hate to disappoint you, but the games that game theory usually studies are much, much simpler and more abstract than the kind of games that you might be thinking of. Okay, so for example, it's definitely not about Fortnite. Okay, so what's a game? Think of a game that's a lot simpler than a video game. Well, you might picture like maybe like a board game. Okay, so for example, chess. But let's think about a game that's even simpler than chess. Even chess is a little bit too complicated. What about what about rock, paper, scissors? Okay, so now we're getting there. Okay, so I'll show you guys a little clip. Okay, show you guys a little clip.
You've all played RPS for a slice of pizza. Imagine playing for a slice of pizza encased in 24-karat gold.
And here comes New England Sean Wicked Fingers Sears. The crowd still hates him even though he's won 12 straight throws since inconceivably switching to his left fist. And while the crowd Sears trade taunts, here comes the Bulldog, the Sarah Palin of RPS, Julie Crosby.
That's right. She was hardly a blip on the RPS radar screen 20 minutes ago, but she's since emerged as a hand sport megastar.
She's also trying to break down gender walls and show that in 2008, a woman can become an RPS champion.
All right, this is it. One of you will be $50,000 richer in just a few minutes.
The bout we've been waiting for. Here we go. Sears throws a textbook paper to jump ahead. Julie, though, slowed the pace, which should work to her advantage.
Wicked Fingers has now won 13 straight throws, an 8,000 to 1 long shot.
And a scissors tie. Though Julie's weak scissors are evidence, fatigue is now a fact.
No, we've all had weak scissors at some point in our lives.
And that tie breaks Sears' perfect streak. And a slick paper gives Sean the first set. His left hand has been absolutely unstoppable. Julie looks a little defeated there. Her husband hasn't given up, though. Let's see how she responds. Julie stops the bleeding with scissors, ironically enough.
Finally, Sean's left hand takes a hit. He's still stoic as Julie looks to tie this match up.
But no, Sean shatters her weak scissors. He's now one throw away from the title, $50,000, and another reason for New Englanders to think they're the greatest. Julie must win this throw to keep the dream alive. She pushes the tempo and wins with scissors. What guts she showed right there.
It's 2 out of 3 for 50,000.
Here comes the biggest moment of anyone's life.
Ready. Engage.
And Julie takes the lead with yet another scissors. I cannot believe what I'm seeing here. The Bulldogs completely turned this match around, and now it's she, one throw from taking it home.
I think I'm going to faint.
Take a deep breath, Roche. Sears wins with paper. He knew she would throw fourth scissors. It's going to come down to one final throw, one decision worth $50,000.
It is 1-1. One set apiece. One throw for $50,000 and the title. Are you ready? Are you ready? One throw. This is it. Nice and clean. Engage.
To wrap her around the world, Sean Wicked Finger Sears is the 2008 U.S.
All right. I think you all agree that that was pretty stupid. So rock, paper, scissors, or RPS, as they were calling it in that clip. That's a real clip, by the way. There are people who play rock, paper, scissors competitively. So rock, paper, scissors is kind of an ideal game for representing in game theory because it is very, very simple. And so what I have here is a table that sort of, I mean, it is rock, paper, scissors, this table, okay? And so this is a way for us to represent the game of rock, paper, scissors as in a sort of formal or mathematical way, okay? So let's look at what's going on here. So first of all, we have going along the vertical and the horizontal axes of this table, the three choices that can be made by each player. Okay, so here we have player X, okay, choosing one of the rows, so either rock or paper or scissors. And here we have the second player, player Y, of course, who also has those three choices available to him or her. Okay. And what I have written in each cell of the table here are sort of the payoffs or the outcomes that accrue to each player as a result of that particular set of choices. Okay. So, for example, if both players choose paper, let's suppose that both players choose paper, then it'll be a tie, and each player will receive nothing. It'll be sort of 0-0. Okay. Now, what if one player, let's say the X player, chooses paper, and the Y player, the second player, chooses rock? Well, then the payoffs are going to be like here, and here, the first number represents player's X outcome. So in that case, player X would win, okay, because he played scissors against rock, and the second player would lose. Okay. The opposite situation would occur if the first player plays paper, but the second player plays scissors. Then the second player would win. And so I have here 0-1 rather than 1-0. Okay. And so you can see all the different outcomes of rock, paper, scissors are diagrammed in this way. Notice that going down the diagonal here, okay, these three diagonal elements represent both players playing the same strategy, rock, rock, paper, paper, and scissors, scissors. Well, in that case, obviously, there's going to be a tie. And so that's why along the diagonal, we have 0-0 like that. And in the other situations, one of the players will win. So what is the solution to a game like this? What is sort of the optimal strategy to playing rock, paper, scissors? Well, so the answer to that question, okay, the idea of, how do you solve a game involves finding that game's Nash equilibrium. This is that concept that John Nash developed, as you'll recall from that video. And if these Nash equilibria exist for a game, then we would expect that in the real world, players to gravitate towards playing these Nash equilibrium strategies. Okay. And so you might go, how do I find the Nash equilibrium of a game? Well, you sort of go through this process and identify when players are best responding to each other's strategy. Okay, so let me try to illustrate this. So what I'm going to do is I'm going to consider the best strategy for player Y, okay, given that we know what player X is going to play. And I'm going to mark them with a star. Okay, so for example, note that if player X plays rock, then obviously player Y's best response is to play scissors. Or I'm sorry, to play paper. And so, so here's player X playing rock, and then I've marked a little star next to player 2's payoff, okay, to denote that, okay, this strategy, the strategy of paper, is the one player Y should choose. Okay. Similarly, if player X plays paper, then player Y should play scissors. So I've marked this one. And then finally, if player X plays scissors, player Y should play rock. So I've marked this one. Okay, so I've just marked player Y's best response with a star. Okay, so then I'm going to do the same for player X. So I'm going to say, okay, what if player Y plays rock? Then we know that we're in this column. So given that player Y is playing rock, what should the first player play? And we, of course, know that the player 1 should play, in that situation, paper. Okay, and so I've marked a little star next to that payoff. Okay, same thing. If player Y plays paper, then we know that the first player should play scissors. So I've marked this particular outcome. And then finally, if player Y plays scissors, then we know the first player should play rock. So I've marked this particular column up here. Okay, So note that there are no outcomes in this table that have 2 stars. That is to say, there is no strategy which involves the 2 players each best responding to the other one's strategy. Okay? So what that means is that this game, rock, paper, scissors, actually has no Nash equilibrium. A Nash equilibrium would be a situation where after I've done this process, marking these payouts with the stars, that I have something that looks like this, where I have 2 stars for a single cell. Okay? So that never happens with this game. Okay? And this is consistent, of course, with our experience, right? We know that there's no Nash equilibrium for rock, paper, scissors because, well, if there were, then players, as I just told you, they generally speaking, it's always best to choose the Nash equilibrium strategy. But, of course, you know that there is no best strategy in rock, paper, scissors, right? It's not, for example, the case that you ought to always choose rock or something like that, okay? Despite, this is just for fun. Let me show you guys this clip.
Poor predictable Bart always takes rock. Good old rock. Nothing beats that. Rock, paper, dope.
Okay, right? So obviously that would not be a very good way to play rock, paper, scissors. Okay, so...
Unscrew all the Phillips heads?
Oh.
Check. Did you unscrew all the...
All right, close it. Okay, so now... So interestingly, okay, although rock, paper, scissors does not have a Nash equilibrium in the manner that I've just described, it actually does have a Nash equilibrium in mixed strategies. Okay, so it has no, so I shouldn't say that it doesn't have a Nash equilibrium. It has no Nash equilibrium in pure strategy. So pure strategy is when you're going to play a particular strategy 100% of the time. Okay, but it does have a Nash equilibrium in mixed strategies. So mixed strategy, as the name suggests, is when you mix up your strategy and play each strategy only some percent of the time. It's sort of a more randomized way to play. Okay, for example, a mixed strategy would be to play rock 50% of the time and paper and scissors each 25% of the time. Okay, now there is a Nash equilibrium for rock, paper, scissors if you allow for mixed strategies. And that Nash equilibrium is for each player to play each strategy exactly 1/3 of the time. Exactly 1/3 of the time. Okay, so if you want to know what the optimal strategy is for rock, paper, scissors, okay, well, the Nash equilibrium strategy is basically to completely randomize. Okay, to play each choice only 1/3 of the time. Okay, so the point is, so finding these Nash equilibrium, okay, it's not necessarily about finding the best strategy for a single player. What you do is you go through this sort of analysis of each player's best response in the manner that I've just shown, and at the end you discover a property of the game itself. Okay, and we'll find that the various types of games that we're about to consider have different Nash equilibria. By the way, the reason why Nash is so famous is because he proved that once you allow for these mixed strategies, all games in the very general way that games are defined, all games have at least one Nash equilibrium. Okay, so hopefully that example makes sense. Okay, that's rock, paper, scissors as a formal game. And we'll talk about some other more interesting and more important games besides rock, paper, scissors in the next